Earth is special because it hosts life and a developed civilization. But the universe holds many other fascinating objects you may never have heard of. Very few of us realize that the universe is largely empty, with more than 99% of its volume made up of vast open space. And that fact can feel unsettling, sending a shiver through us in a quiet, unfamiliar way. When we look up at the night sky, we are usually drawn to the light: stars, nebulae, galaxies. Yet behind all those points of brightness lies a much quieter truth. Most of the universe is not light, and it is not matter. What caused the universe to be built this way? Why does emptiness dominate? And why is this not only a scientific fact, but something that touches an ancient human fear? The fear of separation, of isolation within infinite space. If you feel curious, leave a comment, like, share, and subscribe to join us. Now, relax your breathing and prepare to step into a journey exploring the emptiness that is shaping the fate of the universe. At first glance, the universe can feel crowded. When we look up from Earth, the night sky appears scattered with light, and photographs from telescopes seem packed with stars, clouds, and distant galaxies. It is easy to carry the quiet assumption that space is full, layered with objects in every direction. Yet when we linger with the larger picture, another reality slowly comes into focus. As we drift outward in scale, we notice how quickly those points of light fall away from one another. The spaces between them widen, the glow thins. What remains is not more structure, but distance. The universe we inhabit is not defined by what is present, but by how much is absent. If we gather everything familiar into a single thought, every body, every planet, every star, every glowing nebula, the total is surprisingly small. All of it together forms only a tiny fraction of what exists. Spread evenly across the universe, ordinary matter becomes almost vanishingly thin. On average, there are only a few simple atoms in a space as large as a room. Between galaxies, even those few are often missing. You can sense the contrast by imagining the air around you. Each breath carries countless particles through a volume far smaller than the gaps between galaxies. In intergalactic space, that same volume is nearly empty. Nothing moves through it, nothing gathers there. It is not waiting to be filled. It already represents the default state. Even when we compress the view further, collecting all observable galaxies, each containing billions of stars, the result barely occupies any space at all. If every luminous structure were drawn together, the combined volume would still be negligible compared to the vastness that surrounds it. Most of the universe would remain unchanged, wide and open, untouched by light. Measurements refine this impression. The matter made of atoms, the kind that forms stars and worlds, accounts for only a small share of the cosmic total. The rest is dominated by components that do not shine. Dark matter adds mass without light, shaping how galaxies gather. Dark energy outweighs both, influencing how space itself behaves. In this accounting, what we directly experience is a minority presence. From this perspective, emptiness is not a gap between important things. It is the background. Structure appears as a brief concentration against a much larger openness. Our existence unfolds within one of those concentrations, but the wider universe does not revolve around it. Space does not surround matter. Matter appears within space. As we let this settle, another pattern emerges. Even this sparse matter is not scattered at random. On the larger scales, galaxies trace out long, delicate paths. They gather into narrow strands and thin walls, stretching across immense distances. Between these strands lie regions where almost nothing resides. This arrangement is often called the cosmic web. It is not woven intentionally, but shaped by gravity acting patiently over billions of years. Dark matter forms an invisible framework, guiding ordinary matter along its paths. Where gravity draws material inward, filaments grow brighter. Where matter flows away, vast empty regions remain. The result resembles a foam seen from far away. Thin surfaces outline enormous bubbles. The surfaces hold nearly all the material, while the interiors stay open and quiet. Galaxies trace the edges. The bubbles themselves, the voids, take up most of the volume. These voids are not accidents. They are the natural outcome of structure forming at all. As matter gathers into filaments, space opens elsewhere. Gravity does not fill the universe evenly. It sharpens contrast, leaving some regions rich and others sparse. The emptiness is shaped, not random. As we move deeper into this picture, the voids begin to feel less like background and more like participants. They are not passive gaps. They grow as structures sharpen. Over time, they occupy an increasing share of the universe, quietly expanding while matter retreats into tighter clusters. This growth is tied to another influence, one that becomes more noticeable as space thins out. Between every galaxy, every star, and every atom, space itself is expanding. This expansion does not require motion through space. It is the stretching of space. The farther apart two regions are, the faster that distance increases. The force associated with this behavior is known as dark energy. It does not pull things together. It encourages separation. As space grows, dark energy remains present, guiding the expansion forward. Over time, it becomes the dominant influence on the large-scale behavior of the universe. In practical terms, this means that islands of matter drift away from one another. Nearby systems remain bound by gravity, but distant ones slowly recede. The web stretches. Filaments thin. Voids widen. The universe favors openness over connection. This is not a change waiting far in the future. It is already happening. At this very moment, the space between distant galaxies is increasing. The effect is subtle at small scales, but over millions of light years, it becomes clear. Distances grow steadily, second by second. We can translate this motion into a simple image. Take two galaxies separated by a vast span of space. With each passing second, the gap between them becomes slightly larger, not because either galaxy accelerates through space, but because the space between them changes. The increase is constant and unhurried, yet persistent. This leads to a realization that quietly reshapes the story. The emptiness is not approaching. It is already here. The universe is not becoming empty in the distant future. It has always been mostly empty, and the balance continues to shift in that direction. When we say that the void is prevailing, it is not a declaration of conflict. It is a description of tendency. Structure forms briefly, shines for a time, and then gradually yields to separation. The background state reasserts itself through patience rather than force. From here, every detail we encounter carries this context. The largest voids, the fading of distant galaxies, the limits of observation, all reflect the same underlying pattern. Space dominates. Matter gathers only temporarily. Connection gives way to distance. As we continue forward, we do not leave structure behind. We carry it with us, held lightly against the vast openness that surrounds it. The universe unfolds, as it always has. Wide, sparse, and slowly drifting, with islands of light suspended within a much larger, quieter expanse. And as this realization settles in, the journey continues naturally, moving deeper into the regions shaped by this openness, where the web stretches thinner and the voids begin to define the character of everything that follows. As our instruments slowly extended their reach, we began to learn that seeing the universe clearly was not a matter of speed, but of waiting. Light had to be gathered patiently, night after night, year after year, as telescopes traced the sky in careful sweeps. Some of the most revealing surveys did not rush from one discovery to the next. They moved steadily, allowing distant galaxies to leave faint impressions over long stretches of time. By the early years of this century, one such effort had quietly recorded the positions of more than 1 million galaxies, spread across distances so vast that everyday scales no longer offered guidance. What appeared was not disorder, but pattern. When those points of light were placed into depth, the view changed again. Galaxies did not fill space evenly. They aligned into long, delicate threads and wide, translucent sheets, stretching farther than any single image could show. Between these structures lay enormous open regions, rounded and expansive, where very little appeared at all. Some of these regions were so wide that light would take longer than the entire history of Earth to cross them. As the map took shape, we could sense that emptiness was not something left over. It was the main feature. These surveys quietly shifted understanding. The idea of a cosmic web moved from illustration to measurement. It was no longer only something seen in simulations or imagined from theory. It emerged directly from the data, from countless individual galaxies whose positions and motions lined up into a coherent whole. The voids between filaments were not rare interruptions. They filled most of the volume, repeating again and again across the mapped sky. A subtle tool made this possible. By noticing how the light from galaxies stretched as it traveled through expanding space, astronomers could estimate both distance and motion at once. Each small shift carried information about how far away a galaxy was and how space itself had changed along the way. Over time, these measurements accumulated into a three-dimensional picture. Walls, filaments, and empty regions appeared without being imposed. We did not draw the structure. It revealed itself. When we linger inside these empty regions, their scale becomes difficult to hold in mind. In a typical void, there might be only a single galaxy drifting within a volume so large that comparison loses meaning. You can imagine a region millions of light years across in every direction, holding just one faint island of stars. In our own surroundings, dozens of galaxies share a much smaller space. The contrast is immediate and unmistakable. This difference is more than a matter of degree. It reflects environments shaped by gravity in very different ways. Near us, galaxies interact over long periods. They orbit, merge, and influence one another, slowly reshaping their paths. Inside a void, encounters are rare. Galaxies, when they appear at all, tend to remain isolated, evolving with little interruption from their surroundings. These regions quietly underline how particular our own location is. We find ourselves in a bound group, connected to a wider filament, with other clusters not too distant in cosmic terms. This setting allows for repeated interactions over billions of years. Voids offer the opposite condition, where space outweighs matter and connections seldom form. To understand how such contrasting regions came to be, observation alone was not enough. Researchers turned to large simulations, beginning with conditions inferred from the early universe, when matter and radiation first parted ways. In these models, matter started out almost evenly distributed, marked only by slight variations. Gravity was then allowed to act, step by step, across immense spans of simulated time. What unfolded inside these calculations closely mirrored what telescopes now observe. Matter drifted toward regions that were just a little denser, gradually strengthening filaments and clusters. Other areas slowly emptied as material flowed away, leaving behind wide voids. No extra forces were needed. Gravity, working within an expanding universe, was sufficient to produce the web. These simulations include both dark matter and dark energy, with proportions guided by observations of the early universe's faint background glow. When these elements are combined, the resulting structures align closely with survey data. The cosmic web appears not as an exception, but as a natural outcome of simple conditions unfolding patiently. From this viewpoint, voids are not mistakes or gaps where structure failed. They are the counterpart to filaments. As matter gathers along narrow paths, space opens elsewhere. The universe separates itself into regions of relative abundance and regions of pronounced scarcity, each emerging from the same process. As attention turned more closely to these empty regions, small differences began to stand out. Some voids seemed to widen slightly faster than gravity alone would suggest. Surveys designed to trace dark energy, by studying galaxy distributions and the bending of distant light, began to hint at this effect. These observations point toward a subtle role for dark energy within voids themselves. Where matter is scarce, there is little to counteract expansion. Space stretches more freely, and the interiors of voids thin further, as their boundaries drift outward. Over time, these regions grow not only larger, but more dominant. In a few cases, the presence of especially large voids can be sensed indirectly. As ancient background light passes through them, it undergoes small changes that can be measured statistically. These signals are faint, but they provide another way to trace how emptiness evolves across vast distances. None of this overturns the broader framework of cosmology. Instead, it adds texture. Dark energy appears not only as a uniform influence, but as something whose effects become clearer where matter retreats. Voids become places where expansion shows itself most plainly. Across all these findings, one theme continues to surface. The universe organizes itself through contrast. Dense regions slowly grow denser, while empty regions continue to open. Mapping the cosmic web does not reveal balance, but a steady leaning toward openness. We can pause within this mapped view. Filaments extend across immense distances, linking clusters like narrow bridges. Around them, voids spread quietly, occupying most of the space. Nothing here rushes toward an ending. The pattern keeps unfolding, shaped by forces that act evenly and without haste. The maps do not point toward a final arrangement. They show a process already in motion, becoming clearer as observations deepen. Each new survey adds detail, yet the overall impression remains unchanged. Space dominates. Structure traces thin paths within it. As time continues forward, this emphasis grows stronger. Voids widen, filaments thin, and bound regions stand out as brief concentrations within a much larger openness. The web remains, but its threads slowly lose contact with one another. From here, it feels natural to turn toward particular examples, places where this pattern reaches its extremes. Some voids are so large that they stretch intuition even further. They offer another way to sense scale and distance, and to follow the quiet persistence of expansion as it carries the universe onward, without a sharp boundary or a final turn. Among the many empty regions traced by surveys, one stands out for its scale and clarity. In the direction of the constellation Boötes, astronomers identified a vast region where galaxies are strikingly scarce. This discovery did not come from a single image, but from careful measurements of distance and motion, galaxy by galaxy, until a pattern emerged that could not be ignored. In the early 1980 seconds, while measuring redshifts in this part of the sky, researchers realized that an enormous volume contained far fewer galaxies than expected. The region stretched across hundreds of millions of light-years. Where thousands of galaxies might normally appear, only a small number could be found. The space between them dominated the view. What had seemed like an ordinary direction in the sky revealed itself as one of the largest known voids. This region came to be known as the Boötes Void. Its size alone makes it remarkable. Light crossing from one side to the other would need a span of time comparable to much of cosmic history. Within that distance, matter thins almost to absence. The void does not mark a sharp boundary. Instead, galaxy density decreases gradually as one moves inward, until the interior feels almost untouched by structure. Boötes offered a clear demonstration that the universe allows extremes. The cosmic web contains filaments and clusters, but it also permits regions where those features nearly vanish. Such emptiness does not violate known laws. It emerges naturally from the same processes that build structure elsewhere. Yet, encountering it directly challenges intuition, because it reveals just how dominant open space can be. To imagine living inside such a region is to imagine a very different sky. If a galaxy like the Milky Way were placed near the center of the Boötes Void, neighboring galaxies would be rare sights. The familiar pattern of clustered companions would be missing. Even with powerful instruments, only faint, distant smudges would appear, scattered thinly across darkness. In such a setting, inferring the larger universe would be difficult. With few nearby galaxies to compare, the sense of being part of a vast web would be muted. The sky would not obviously suggest filaments or walls extending beyond view. A civilization there might understand stars and their own galaxy in detail, yet struggle to reconstruct the broader cosmic arrangement. This thought experiment highlights a subtle point. Our understanding of the universe is shaped by location. We reside in a region rich enough in nearby galaxies to reveal patterns. The cosmic web appears clear to us, in part because of where we are. Botez shows that other perspectives are possible, shaped by scarcity rather than abundance. The existence of such a void invites questions about its origin. One explanation fits comfortably within established models. In the early universe, matter was not perfectly uniform. Some regions were slightly denser, others slightly thinner. Over billions of years, gravity amplified these differences. Areas that began with lower density gradually emptied as matter flowed outward, forming a large void. In this view, Botez represents an extreme case of an underdense region, expanded and clarified over time. Dark energy, which influences the expansion of space, would have assisted this process by allowing the void to widen more easily once matter became sparse. Nothing exotic is required, only patience across cosmic time. Another possibility has also been considered. Dark energy might not behave identically everywhere. If its influence varies slightly across space, some regions could experience expansion more strongly than others. In such areas, matter would be pushed outward more efficiently, deepening and enlarging voids beyond typical expectations. Current observations cannot yet distinguish cleanly between these ideas. Large surveys continue to map millions of galaxies, looking for subtle patterns that might reveal whether dark energy changes with position or time. Extreme voids like Botez serve as natural laboratories, places where the effects of expansion stand out clearly because so little matter remains to counter them. What matters for the broader picture is not which explanation ultimately prevails, but what Botez demonstrates. The universe does not resist large-scale emptiness. It accommodates it, and in some cases, amplifies it. The same forces that create clusters also allow vast regions to empty almost completely. For this reason, Botez can be seen as a preview rather than an exception. As expansion continues, distances between galaxy groups grow. Bound systems remain intact locally, but connections across larger scales weaken. Over immense spans of time, each cluster becomes increasingly isolated, surrounded by expanding space. In that distant future, the overall appearance of the universe would resemble an enormous void filled with small islands of matter. Each island would contain its own stars and remnants, while the space between them would stretch beyond communication. In that sense, Botez reflects a pattern that becomes more common with time. This perspective does not point to a sudden change. It describes a slow progression already underway. The universe does not transform abruptly into emptiness. It gradually emphasizes what has always been true, that most of its volume is space, and that structures are temporary concentrations within it. Botez helps place this trend into a tangible form. Instead of an abstract future, it offers a present-day example. By observing it, we glimpse how large-scale expansion shapes environments and how location influences perception. The void is not a signal of collapse or failure. It is an expression of how the universe distributes itself. Within this view, emptiness is not opposed to structure. It is paired with it. As clusters gather, voids grow. As filaments sharpen, open regions widen. The balance shifts gently, without conflict, following the same underlying principles everywhere. As attention moves beyond Botez, other large voids and subtle imprints come into focus. Together, they continue the story, showing how expansion, dark energy, and structure interact over time. The universe carries on in this pattern, revealing more of its openness as distances slowly increase, with no final boundary, only ongoing change. As the maps of voids became clearer, attention turned to the influence behind them. The widening of empty regions was not only a matter of gravity drawing matter into filaments. Another factor was at work, subtle yet persistent, shaping the large-scale behavior of space itself. Understanding this influence required looking back to an unexpected discovery near the end of the 20th century. In the late 1992s, astronomers studying distant stellar explosions noticed something unusual. These events, known as Type Ia supernovae, shine with a predictable brightness. Because of this consistency, they serve as reliable distance markers across the universe. When teams measured how bright these supernovae appeared, they expected to confirm a slowing expansion, pulled back by gravity over time. Instead, the data pointed in the opposite direction. The supernovae were dimmer than anticipated, implying they were farther away than a slowing universe would allow. Space was not easing its expansion, it was increasing its pace. This realization reshaped cosmology. The expansion of the universe was accelerating, not decelerating. To account for this behavior, scientists introduced the concept of dark energy. It was not observed directly, but inferred from its effects on cosmic expansion. This addition resolved the discrepancy between expectation and measurement, and it transformed the standard model of the universe. Expansion driven only by matter and gravity was no longer sufficient. This discovery echoed an idea from much earlier. Decades before, Albert Einstein had modified his equations of gravity by adding a term known as the cosmological constant, represented by the symbol L. He originally introduced it to allow a static universe, which was the prevailing assumption at the time. When expansion was later observed, he removed the term, believing it unnecessary. With the discovery of accelerated expansion, the cosmological constant returned, now with a different meaning. Rather than holding the universe still, it described a tendency for space to expand on its own. In modern cosmology, L serves as a mathematical expression of dark energy, fitting neatly into a framework that matches observations from many directions. Measurements of the cosmic microwave background, distant supernovae, and the bending of light by massive structures all converge on a similar picture. Most of the universe's energy content is associated with dark energy. Dark matter contributes additional mass without light, and ordinary matter forms only a small remainder. Together, these components define the evolution of cosmic structure. Dark energy behaves differently from matter. As the universe expands, matter spreads out and becomes thinner. Dark energy does not dilute in the same way. It is often described as a property of space itself. As space increases, the total amount of dark energy increases with it, while its density remains nearly constant. This behavior has important consequences. Expansion driven by dark energy does not fade with time. Instead, it persists, and over very long spans, it becomes the dominant influence on cosmic motion. Galaxies that are not bound together by gravity gradually separate at increasing rates, not because they are moving faster through space, but because space between them is changing. In regions where matter is sparse, this effect is especially clear. Voids, already low in density, experience expansion with little resistance. Their interiors widen steadily, and their boundaries drift outward. Over time, the contrast between dense regions and empty ones becomes more pronounced. One outcome of this process is the formation of a cosmic event horizon. There exists a distance beyond which the expansion of space carries regions away faster than light can traverse the growing separation. Light emitted from beyond this boundary will never reach us, no matter how long we wait. This horizon is not fixed. It depends on the balance between expansion and time. As dark energy continues to shape expansion, this horizon defines the limits of what can be observed or influenced. Galaxies approach it gradually. Their light becomes more stretched, their signals weaker, until they fade from view entirely. They do not vanish abruptly. They simply slip beyond reach. This narrowing of the observable universe is a physical process, not a matter of perception alone. It reflects how space-time itself evolves. The universe does not hide information deliberately. The structure of expansion determines what connections remain possible and which slowly dissolve. Over immense spans of time, the effect becomes clear. Bound systems, such as galaxy groups and clusters, remain intact. Gravity holds them together against expansion. Beyond these islands, however, separation increases. Eventually, only the nearest structures remain visible. Far in the future, observers within a bound group like our own would see a night sky containing only the galaxies held together by gravity. the wider web would no longer be apparent. Evidence of countless distant galaxies would have crossed beyond the horizon long before, leaving no trace in the observable sky. This future perspective highlights how much our current view depends on timing as well as location. We live during an era when expansion has not yet erased the broader structure from sight. The cosmic web is still visible, and the background glow from the early universe still reaches us as a faint afterimage. Dark energy does not bring this change suddenly. It works evenly and persistently. Its influence accumulates through time, guiding expansion toward greater separation and wider emptiness. The universe trends toward a state where energy is spread thinly. Interactions become rare, and structure exists mainly within isolated regions. This long progression aligns with the idea of a gradual fading future, often described as heat death. It does not involve sudden events or sharp transitions. It reflects a steady movement toward balance, where energy differences diminish and activity slows across vast scales. Within this framework, the shrinking horizon is not an ending, but a feature of ongoing evolution. It shapes what can be known, seen, and connected. The universe continues to expand, guided by simple principles that act without haste. Dark energy, the cosmological constant, and the event horizon together provide a coherent picture. They explain why voids widen, why distant galaxies drift away, and why the observable universe is only a portion of something larger. The cosmos remains open-ended, unfolding over times far beyond immediate concern, carrying its structures forward as space itself continues to grow. As the picture of an expanding and increasingly separated universe settles in, another question has often surfaced alongside it. It does not arise from telescopes alone, but from scale and time taken together. In a cosmos with vast numbers of stars and planets, and with billions of years available for change, one might expect signs of others to appear, yet the sky remains largely unchanged by any obvious traces of technological activity. This question was voiced clearly in the middle of the 20th century. During a casual conversation, the physicist Enrico Fermi noted the apparent mismatch between expectation and observation. With hundreds of billions of stars in our galaxy alone, and many more galaxies beyond, the absence of clear evidence seemed puzzling. His simple phrasing captured it. Where is everybody? Modern astronomy has added detail to this backdrop. Observations of planets around other stars show that planetary systems are common. Many stars host worlds, and a fraction of those orbit at distances where liquid water could persist under suitable conditions. Some of these stars are far older than our Sun, offering long spans of time for change and development. From a distance, it can appear that conditions favor abundance. Large numbers of stars, many planets, and deep time together suggest opportunity. If intelligent life were widespread and inclined to leave lasting marks, traces might be expected in the form of signals, large structures, or unusual patterns in astronomical data. Yet decades of observation have not revealed such signatures in a convincing way. This contrast between expectation and observation forms what is known as the Fermi paradox. It is not a contradiction in physics, but a tension between scale and silence. The paradox does not demand a single answer. Instead, it has opened space for many possibilities, each reflecting different assumptions about life, intelligence, and survival. One family of ideas is often grouped under the name Great Filter. This term refers to barriers that are difficult to cross in the long chain, from simple chemistry to visible, long-lived civilizations. These barriers could occur at many stages. The emergence of life itself might be rare. The development of complex cells could be uncommon. Intelligence might arise infrequently, or technological societies might not persist for long. In this view, the silence is not surprising. It reflects the difficulty of passing through a sequence of transitions, each with its own challenges. Some versions place the most difficult steps far in the past, suggesting that surviving to this point is already unusual. Other versions consider major barriers ahead, implying that many civilizations do not remain detectable for extended periods. The idea does not rest on a single mechanism. It encompasses biological limits, environmental instability, and the constraints imposed by physics and time. It does not require dramatic endings or sudden failures. Gradual loss, changing priorities, or limited expansion could all reduce visibility without leaving obvious traces. Another perspective considers how quickly a technological civilization might spread, if it chose to do so. Even at speeds well below that of light, models suggest that a wave of exploration or influence could cross a galaxy in a span that is short compared to the galaxy's age. In this context, 1,000,000 years is a brief interval. Compared to the billions of years that galaxies have existed, such timescales are modest. This contrast sharpens the puzzle. If expansion was straightforward and common, the absence of clear evidence becomes harder to explain. The question then shifts from whether expansion is possible to whether it is typical, sustained, or even desired. Against this backdrop, organized searches have taken place. Programs dedicated to listening for signals or scanning for unusual astronomical features have operated for decades. Early efforts focused on narrow radio bands. Later projects expanded their reach, surveying wide ranges of frequencies and directions with increasing sensitivity. More recent initiatives have processed enormous volumes of data, examining countless signals and filtering out natural sources. In parallel, astronomers have searched for indirect signs, such as large-scale energy use or altered planetary atmospheres. So far, every confirmed signal has found an explanation in known astrophysical processes or terrestrial interference. This accumulated quiet is not the result of inattention. It reflects sustained effort and improving tools. Each generation of instruments extends the search, yet the outcome remains the same. No clear markers of technological activity have been identified beyond Earth. Placed alongside the earlier chapters, this silence takes on a broader context. The universe is not only large, but increasingly separated. Expansion driven by dark energy gradually limits contact across vast distances. Even if civilizations arise, the structure of space-time itself narrows the window during which they could interact or be observed. In such a universe, absence of evidence does not point to a single conclusion. It may reflect rarity, brevity, separation, or timing. Isolation increases naturally, without requiring dramatic events or universal outcomes. Seen this way, the Fermi paradox becomes less a mystery demanding resolution and more a reflection of scale. Space is wide, time is deep, and connections are fleeting. The lack of detected signals fits comfortably within a universe where emptiness dominates and separation grows steadily. The long search continues quietly, guided by patience rather than expectation. It unfolds within the same cosmic conditions that shape voids and horizons. Whatever the ultimate explanation, it will be constrained by these conditions, shaped by expansion, distance, and the slow thinning of structure. As the universe continues on its course, the question of others remains open, held lightly within a setting that does not hurry toward answers. The sky stays largely unchanged, and the background of space carries on, wide and uninterrupted, as observation and time move forward together. We often picture a meeting between civilizations as something that might happen somewhere out there, if we just look long enough, as if the universe were a big room and the main problem were distance. But as we drift further into this story, another dimension slowly becomes important. It is not only about where others might be, but when. Time, stretched across cosmic scales, quietly narrows the chance that two distant minds ever share the same moment. On human scales, 1,000,000 years feels almost endless. On cosmic scales, it is a brief flicker. A star like the sun can shine for billions of years. Galaxies have existed for more than 10 billion. Against that background, even a long-lived civilization, one that survives for hundreds of thousands or 1,000,000 years, occupies only a thin stripe in the timeline of its star and an even thinner one in the history of its galaxy. It appears, changes its surroundings for a while, and then yields to whatever follows. You can imagine these lifetimes as scattered stripes on a long axis of time. Some begin early, near the youth of their stars. Others appear later, close to the end of stable eras. Between them lie stretches where no technology exists, only planets reshaped by weather, impacts, and slow geological processes. If two stripes do not overlap, there is no shared present, no possibility of exchange. Even if the galaxies involved once held thriving worlds, even here, on Earth, the record of our own activity reminds us how fragile traces can be. Over a few centuries, buildings crumble if they are not maintained. Over millions of years, continents shift, mountains erode, and oceans advance and retreat. Craters fade, minerals reform, and rock cycles through deep interiors and back again. On worlds with active surfaces, the marks of technology do not last long when measured against planetary time. On quieter planets, without strong tectonics, surfaces can remain more stable, but they are still exposed to impacts, radiation, and slow chemical wear that gradually smooths away detail. In that context, a civilization that rises and falls millions of years before another will leave few, if any, recognizable signs. Its signals will have washed through space and thinned into background noise. Its structures will have blended into natural geology. Its artificial atmospheres, if they ever existed, will have relaxed back toward chemical balance. What remains is a world that looks ordinary, holding a history that is no longer legible. The question becomes less, where are they in space, and more, where were they in time? Layered on top of this misalignment is the steady expansion of the universe itself. Space between galaxies is stretching. When we consider a galaxy billions of light years away, even a simple exchange of messages begins to feel out of step. A signal sent from one side would take billions of years to arrive. Any reply would require another span of similar length. By the time the full round trip completed, both civilizations might have changed beyond recognition or simply ceased to exist. Expansion adds another quiet complication. As space stretches, the wavelengths of signals traveling through it also stretch. A focused radio message becomes more spread out, its energy diluted over a larger region and shifted to longer wavelength. Detecting such a signal at great distance requires not only sensitivity, but fortune. The right instruments, at the right time, pointed in the right direction, while both sender and receiver still exist. The window for contact narrows further. When dark energy dominates, this process becomes even more pronounced. Distant galaxies recede faster as separation grows. There is a threshold beyond which even light cannot bridge the growing gap in a finite time. Regions drift outside one another's reach, not because they move through space too quickly, but because space between them expands too rapidly. Communication with such regions is not just unlikely, it becomes physically excluded by the structure of space-time. Taken together, misaligned lifetimes and expanding distance paint a different picture of the universe's silence. Our galaxy may have hosted many technological eras scattered across its long history, each confined to its own brief corridor of time. Signals from those eras would have flashed outward, traveled for a while, and then continued on through an ever-thinning web of receivers. By the time we began to listen, their echoes may have slipped past or faded below detectability. In this view, a galaxy can be full of past activity, yet present itself as quiet. The stars hold their orbits, the gas and dust follow the patterns set by gravity, but the civilizations that rose and fell within that framework no longer share our moment. You can imagine the Milky Way as containing many layers of experience, stacked across time, with only one thin layer currently active. We inhabit that layer. Others, if they existed, lie above or below, unreachable. When we fold probability into this image, the overlap becomes rarer still. Even if many civilizations arise over the life of a galaxy, each with its own duration, the chance that two of them exist at the same time, within practical signaling distance and with compatible technologies, becomes small. Add the effects of expansion, redshift, and the steady narrowing of what regions can respond to one another, and the interval shrinks further. The silence we observe may be less a sign of absence and more a reflection of timing. The future of observation adds another layer. As expansion continues, more distant galaxies drift beyond our event horizon. their light grows fainter and more stretched, until it no longer reaches us at all. Over very long spans, only the galaxies bound to our local group will remain visible. The wider web will slip away, not through an abrupt change, but through slow retreat beyond our reach. In that distant epoch, astronomers looking outward from within a small cluster of bound galaxies would see a sky that suggests a much smaller universe. Without access to the background glow from the early cosmos and without visible evidence of receding structures, they might reasonably conclude that space is static and limited, containing only a modest set of islands in a dark sea. The clues that support our current picture of a large, expanding universe would have faded. This idea is sometimes described as a kind of cosmic forgetting. It does not involve any decision or intention. It is simply a consequence of horizons and time. As information about the broader universe stops arriving, models that depend on that information can no longer be tested. The cosmos becomes harder to read, not because it is less structured, but because its structure has moved beyond observation. From where we stand now, we occupy a narrow interval when many threads still intersect. The cosmic microwave background still reaches us. The large-scale structure of galaxies can still be mapped. Signals from our own world can still travel outward into a space that has not yet closed around us. This is not a special privilege in a moral sense. It is a temporary alignment of conditions. In such an interval, listening and not hearing becomes part of the story rather than a contradiction. The quiet sky sits naturally within a universe where lifetimes rarely overlap, where signals must cross expanding distances, and where horizons slowly redraw what can be known. The window for meeting others is real, but it is thin in time and narrow in space. As expansion continues and eras turn over, that window changes shape, and the cosmos keeps unfolding, with or without shared moments between distant minds. A small bubble in a wider ocean. When we picture the universe, it is easy to imagine that what we see in our deepest images is all there is. Maps of galaxies, measurements of distant light, and simulations of cosmic structure give a feeling of completeness, as though we are tracing the full extent of reality. Yet all of this sits inside a limited region, shaped not by imagination, but by the speed of light and the time that has passed since the universe became transparent. Around us lies what we call the observable universe, a sphere defined not by matter or walls, but by time. Light has been traveling since the early moments after the Big Bang, and in that time it has crossed a finite distance. Because space has been expanding, that distance, expressed today, reaches out to a radius of around 46 billion light-years. Within that bubble, light has had just enough time to arrive. Beyond it, signals are still on their way or will never reach us at all. Everything we measure, every galaxy we map, every subtle variation in the cosmic microwave background comes from inside this region. It is a generous volume by human standards, holding hundreds of billions of galaxies and an intricate web of structure. Yet compared with the possible extent of the full cosmos, it may be no more than a small patch, a local neighborhood in a space that continues far beyond our horizon. The true size and shape of the universe outside this bubble remain uncertain. It may extend without bound, or it may curve back on itself over scales larger than we can currently observe. It may be nearly uniform, or it may vary in ways that would alter our understanding of physics if we could see far enough. Whatever lies beyond the observable boundary is, for now, part of a wider ocean whose waves never reach our shore. This limitation is not a temporary inconvenience. It arises from the basic structure of space-time. Light needs time to travel, and that time is finite. As the universe continues to expand, more distant regions move effectively out of contact. The line between knowable and permanently out of reach becomes an enduring feature, shaped by the same dark energy that drives the widening of voids. Within our bubble, we reconstruct history from faint signals. The cosmic microwave background carries an imprint from a time when the universe was young and dense. Large-scale surveys map how matter has arranged itself into filaments and voids. Together, these observations allow us to build a coherent story about how structure formed and how expansion has evolved. Yet they remain, in the end, a partial archive. Many events may have occurred outside our horizon, leaving no trace in the light that reaches us. Whole regions of space, with their own histories of star formation, structure, and change, may never contribute a photon to our detectors. There could be variations in the behavior of dark energy or in the distribution of matter on scales too large for us to sample. If such differences exist, they remain unrecorded in our data, simply because their signals cannot arrive. At the same time, within our observable region, emptiness itself is reshaping what can be known. As dark energy drives expansion, voids widen and deepen, filaments thin as matter drifts outward, and clusters become more isolated. This is not merely a rearrangement of galaxies. It is also a quiet erosion of structure, an ongoing simplification of the patterns from which we read the universe's story. Information about the cosmos is encoded in structure, in the way galaxies cluster, in the temperature ripples of the microwave background, in the delicate alignments that reveal how matter bends light. As the universe evolves, many of these patterns become harder to access. Light grows fainter and more stretched. Distant galaxies fade beyond detection thresholds. Signals that once carried detail merge into a smoother background. In this sense, voids are not only empty regions, they are part of a process that dismantles complexity. As they grow, they dilute the contrasts that make structures clear. Over immense timescales, this trend leads towards states where differences are muted and information is more difficult to extract. Entropy, the measure of how widely and evenly energy is spread, increases as structures lose definition. The expansion of empty space creates more of itself. And with each step, the universe becomes slightly more uniform on the largest scales. The cosmic web that now stands out so vividly in simulations and surveys is a transient arrangement. Its filaments and walls are subject to the same tendencies that favor openness over clustering. As matter drifts and interactions become rarer, the distinctiveness of these features softens. From our vantage point, we observe the universe at a time when the balance between structure and emptiness still preserves a rich archive. The microwave background is still bright enough to map. Distant galaxies still contribute measurable light. Gravitational lensing still reveals the distribution of invisible mass. These conditions will not last indefinitely. Looking outward, we encounter a boundary set by the speed of light and the age of the cosmos. Looking forward, we encounter another boundary, created by the combined effects of expansion and entropy. In both directions, limitations arise not from instruments or methods, but from the way space-time itself behaves. There are regions we cannot see now, and there will be patterns we cannot see later, even within regions that are currently accessible. The possibility that the universe is larger and more varied than our observable patch suggests is therefore more than a philosophical idea. It is a practical recognition that our data set is incomplete and always will be. Some aspects of reality may lie forever outside our horizon, and some aspects of our own region's history may be blurred beyond recovery by expansion and the growth of voids. Theoretical models explore possibilities beyond what we can test directly. Some imagine universes with different curvatures or varying dark energy. Others propose larger frameworks, in which our observable bubble is one region among many. Observational programs, such as large redshift surveys and future space missions, attempt to probe the behavior of dark energy over time, searching for hints that its influence may change. Even so, there are limits that no observation can cross. These limits do not render our knowledge meaningless. Within the observable universe, patterns are consistent across many lines of evidence. The same parameters that describe the microwave background also explain large-scale structure and the recent acceleration of expansion. The model we use is grounded in what can be seen and measured. It remains a provisional map, accurate within its domain, yet silent about territory beyond its edges. As the universe continues to evolve, the interplay between observable and unknowable regions becomes part of its story. Voids widen, horizons shift, and information is gradually smoothed out. Future observers, living in a more isolated cosmic environment, may find a simpler sky to interpret, with fewer clues pointing back to an early, crowded universe. In that quieter setting, the distinction between what can be inferred and what must remain unknown will sharpen. The traces that now support a detailed narrative of cosmic history will have faded, leaving behind a more limited archive. The universe will still be there, but much of its earlier complexity will have receded beyond both sight and reconstruction. For now, we occupy an interval where the contrast is still visible, where the observable bubble is full of structure, and where the growing influence of emptiness can be traced step by step. Beyond our horizon and beyond our future reach, the larger cosmos continues in ways we can only approximate. Inside our region, voids and expansion work steadily, reshaping what can be known and what must remain part of the unseen background, as the universe drifts onward through its wide and slowly simplifying expanse. Far from any star, in the open reaches between galaxies, space is not completely dark. Everywhere we look, there is a faint glow at microwave wavelengths, the quiet afterglow of the early universe. This background fills all directions with almost the same low temperature, only a few degrees above absolute zero. It is so uniform that it sets a kind of reference level for the cosmos, a shared environment, bathing even the emptiest regions in the same thin light. When observatories map this background across the whole sky, the result looks almost featureless at first glance. The temperature changes only by tiny amounts from place to place, slight ripples that record the conditions of the young universe. These subtle patterns have been measured in detail by satellites and ground-based telescopes, all converging on nearly the same average value. In ordinary intergalactic space, nothing is expected to drift much below that level unless something actively removes energy. That is why one particular region has drawn attention. When astronomers combined deep galaxy surveys with maps of the microwave background, they noticed a patch that appeared slightly cooler than its surroundings. More than simple chance would suggest. Tracing this direction on the sky leads to a vast, underdense region known as the Eridanus supervoid, a volume of space on the order of 1 billion light-years across, where galaxies are unusually sparse. Follow-up observations showed that this supervoid lines up with one of the most prominent cool patches in the background glow. At first, some wondered whether the measurement was an artifact of instrumentation or data processing. As more instruments checked the same area, the feature persisted. The difference in temperature is not dramatic in everyday terms, but in the careful language of cosmology, it is pronounced enough to stand out from the usual ripples. To understand why a void might leave a cooler mark on the background, we can think about how light travels through changing gravitational landscapes. Photons from the microwave background traverse the large-scale structure of the universe, passing through clusters, filaments, and empty regions. As they move through these areas, they briefly feel the pull of mass and the effects of expansion. In a universe where expansion is accelerating, this journey can slightly alter their energy. In the case of a large void, gravity is weaker inside than in surrounding regions, and expansion has more room to act. As background photons enter such a region and then emerge again, they can lose a small amount of energy compared with what simple, static models would predict. This process, known in technical terms as an integrated effect along their path, leaves a faint temperature imprint on the microwave sky. Standard cosmological models already anticipate such small signals. When simulations include dark energy and the known distribution of matter, they predict that voids and clusters together will contribute a pattern of tiny, warm and cool spots on top of the primordial ripples. What makes Eridanus interesting is that the observed cooling appears a little stronger than some calculations suggest, hinting at either an unusually deep underdensity, subtle statistical chance, or physics that is not yet fully captured. The data are still being examined and debated. Some analyses find that the discrepancy is within the limits of cosmic variance, the natural scatter we expect when we only have one universe to observe. Others see the combination of a large supervoid and a relatively strong cold patch as an intriguing clue. In either case, the region serves as a reminder that emptiness is not inert. Even where there is little matter, the interplay of expansion, gravity, and radiation leaves a trace. If we picture a photon of the microwave background crossing this supervoid, its journey takes hundreds of millions of years. For most of that time, it glides through a domain where there are few galaxies, little hot gas, and only the faint scaffolding of dark matter. It spends a long interval far from dense structures, and the expansion of space along its path has slightly more influence than it would in a more crowded area. By the time the photon arrives at our detectors, its wavelength has been stretched just a little more than average, and we record that as a slightly cooler spot. In thermodynamic terms, a void like this can be imagined as a region where the universe is a step further along its long trend toward lower temperature and greater uniformity. There is less matter to hold on to heat, fewer stars to pour energy into their surroundings, and more room for radiation to spread out. The background there is not sharply different from elsewhere, but it quietly illustrates the direction in which the cosmos as a whole is moving. As time passes and stars across the universe exhaust their fuel, the balance between warm, bright regions and cold, empty ones will shift. Small, long-lived stars will continue to shine in isolated pockets of matter, yet around them, the vast expanses of almost empty space will dominate the overall picture. The background glow will drift to longer wavelengths, its temperature inching downward, approaching an increasingly uniform low value. In that remote future, supervoids may resemble the leading edge of this cooling process. They already contain less structure and offer fewer sources of new radiation. Energy flows out of clustered regions and into the broader environment. The difference between warm and cold becomes less about location and more about the presence or absence of ongoing stellar activity, which itself will diminish as fuel is used up. Eridanus, in this sense, is both a specific object of study and a symbol. It shows how large-scale structure, dark energy, and the relic light from the early universe all interact. It also offers a glimpse of the thermodynamic path ahead, where emptiness occupies more of the story and temperature variations become increasingly subtle. The measurements we have today are snapshots taken during a particular era, when the background glow is still strong enough to map, and the contrast between filaments, clusters, and voids is still visible. As expansion continues and the universe grows older, those contrasts will soften. The microwave background will become harder to detect, and the imprints left by structures like Eridanus will fade into an even more uniform sea. For now, though, the cold patch and the supervoid beneath it serve as a quiet marker on that path. They show that even in regions where almost nothing seems to happen, the universe is still evolving, still redistributing energy, still reshaping the balance between matter, radiation, and space. The trend is subtle and patient, moving step by step toward a future in which the cosmos settles into a broad, low-temperature expanse with structure drifting within it, like traces on the surface of an ocean that will continue to cool for a very long time. In the far distance of time, the universe drifts toward a quieter kind of simplicity. Star-forming clouds thin out and disperse. The supply of cold gas that once gathered into bright new stars is gradually used up or heated beyond the point where it can collapse again. One by one, the places where stars are born fall silent. What remains are the long-lived remnants of earlier generations. Faint red stars still shining, old white dwarfs cooling very slowly, neutron stars and black holes moving through a background that grows more dilute with every passing epoch. Over stretches of time that are hard to picture, even those small, stable stars exhaust their fuel. The last red suns, which once promised light for trillions of years, eventually reach the end of their fusion cycles. When that happens, star formation has long since stopped, and the universe enters what cosmologists sometimes call the degenerate era. The bright, active phase of galaxies gives way to a scene filled with remnants. White dwarfs cool and darken, neutron stars spin down, and black holes quietly hold what they have gathered. In that distant future, galaxies are no longer the busy, structured systems we see today. By then, expansion and gravity together have separated them into isolated islands, each cluster or group drifting alone within vast regions of space emptied by time. Within those islands, most of the familiar processes have slowed. Stellar winds fade, nebulae disperse, and even collisions between stars and remnants become rare events against an expanding backdrop. As the ages lengthen further, the universe keeps adjusting. White dwarfs radiate their stored heat away and become cold, non-luminous objects. Neutron stars cool into obscurity. Black holes may merge when chance brings them close, but between such encounters, they simply persist. On even longer timescales, some theories suggest that certain particles might decay, gradually transforming the matter that remains into lighter components. The details depend on physics that is still being explored, but the broad direction is clear. Energy usable for complex structures and processes becomes more and more thinly spread. In this vision, heat death is not a sudden event. It is the limit of an ongoing trend, in which temperature differences diminish, flows of energy weaken, and the ability to sustain intricate structures decreases. The universe does not stop. It continues to expand and to exist. But its large-scale activity settles into a state where almost everything that can happen easily has already taken place. What remains are long, quiet intervals, with only occasional, rare events. Even in such a subdued cosmos, the microscopic world never becomes perfectly still. Quantum theory tells us that fluctuations persist. Small variations in fields and particles that appear and disappear without warning. In ordinary conditions, these fluctuations are a background detail, noticeable only in precise measurements. In a universe where almost nothing else changes, they become one of the few remaining sources of novelty. Some theoretical discussions extend this idea into a speculative realm. If the universe endures for extremely long times, and if these fluctuations continue, then there is a tiny probability that, very rarely, they might assemble matter into brief, complex patterns. In thought experiments, researchers imagine a momentary arrangement of particles that resembles a functioning thinking system, complete with memories and a sense of having experienced a history, even though it formed spontaneously from a nearly featureless background. These hypothetical configurations are sometimes given a name in the literature, and they are used as tools to explore questions about probability, typical experiences, and the nature of observation in an old universe. The scenarios are not predictions in the usual sense. They are more like mirrors held up to our assumptions, asking what it would mean to treat every possible fluctuation on equal footing, no matter how unlikely. When the math is extended to truly enormous timescales, the numbers involved become extreme. Under certain conditions, the total count of such brief, randomly assembled thinking systems could, in principle, grow very large, perhaps even exceeding the number of observers that arose from the gradual, evolutionary history of galaxies, stars, planets, and life. This leads to a tension. If most moments of awareness in the full history of the universe came from such fluctuation-based patterns, what does that imply about how we frame our own experience? Many physicists and philosophers find this conclusion unsatisfying. They point out that our understanding of consciousness is incomplete, and that it may require more than an instant's arrangement of particles. There might be a need for a continuous chain of causes, a history that leads from simpler systems to more complex ones, for experience to be meaningful in the way we usually understand it. A momentary pattern without such a history might not qualify in the same way, even if the configuration looks similar on paper. Others suggest that our cosmological models may need to be set within a larger context. In some versions of a multiverse, for example, regions like ours with active galaxies and ongoing star formation could be produced repeatedly, while extremely old, nearly empty regions are less significant in the full picture. In that case, experiences tied to long causal histories might still dominate, making fluctuation-based observers rare in practice, even if they remain a logical possibility. There is no settled agreement on these questions. They sit at the intersection of physics, probability, and philosophy of mind, where definitions matter, and simple counting may not capture what we intuitively mean by an observer. What the discussion does show is that the far future of the universe is not only a story about the fate of stars and galaxies, it also invites reflection on what it means for information, memory, and awareness to exist in a setting where almost everything else has faded. In all of these explorations, The time scales involved are far beyond any human or planetary horizon. The degenerate era, the slow cooling of remnants, and the speculative consideration of rare fluctuations belong to intervals so extended that they function more as conceptual tools than as predictions with practical consequences. They help us map the possibilities allowed by our current theories, rather than outline events anyone will ever witness directly. Seen in that way, the image of a universe drifting toward heat death is less a forecast to dwell on and more a distant boundary condition. It reminds us that structure and activity are temporary contrasts against a much longer background, and that even in an extremely simple future, subtle processes continue. Fluctuations persist, fields shift slightly. Information, once created, may be redistributed, entangled, or encoded in ways that are still being investigated. From here, attention can naturally move toward the question of how information behaves in such a universe. Black holes, quantum fields, and the fabric of space-time itself become part of that inquiry. The same physics that describes expansion, horizons, and fading starlight also reaches into the problem of whether information can ever truly be lost, or whether it is always carried forward in some form, even when the visible structures that once embodied it are long gone. For most of this journey, we have been looking at matter and space, where galaxies form, how voids widen, how dark energy shapes the future. Underneath all of that sits something more subtle, something that is not a substance, but a description of how everything is arranged. We can call it information, the pattern of where particles are, how they move, how fields and energies are distributed at every moment. In physics, we are used to statements about energy and entropy. Energy, in familiar formulations, is conserved. It changes form, moves from place to place, but the total balance stays steady. Entropy, a measure of how many possible microstates can correspond to what we see macroscopically, tends to increase. Systems drift from special configurations toward more typical ones, spreading energy across more degrees of freedom. Information sits between these ideas. It asks, how precisely could we, in principle, reconstruct what has happened, given what we know now? In quantum theory, the underlying mathematics suggests that information is never truly destroyed. The evolution of a closed system is described as unitary, a term that encodes the idea that the full content of the wave function persists, even as it changes form. Probabilities shift, superpositions evolve, but the complete bookkeeping of the system remains intact. In this view, if we had perfect access to everything, we could in principle infer the past from the present. Black holes challenge this picture in an intriguing way. When matter and light fall across the event horizon, they no longer send signals to the outside. The specific details of what crossed the boundary, its composition, its structure, its history, seem to vanish from view. Outside, we are left with only a few parameters: mass, spin, and charge. The richness of the infalling material appears compressed into a small set of numbers. Stephen Hawking's calculations added another twist. According to his work, black holes are not entirely black. They emit a faint radiation, thermal in character, due to quantum effects near the horizon. Over extraordinarily long timescales, this radiation allows a black hole to lose mass and eventually evaporate. The radiation that escapes carries a spectrum that looks very close to a simple temperature distribution, without obvious traces of the fine details of what fell in. Put together, these features create what is often called the black hole information paradox. If the black hole completely evaporates, and the radiation it leaves behind is purely thermal, then it seems that the information about the infalling matter has been lost. That would conflict with the unitary evolution expected from quantum theory. Resolving this tension has been an active area of thought for decades. Many ideas have been proposed. Some suggest that the information is encoded in very subtle correlations within the outgoing radiation. Others point to the holographic principle, in which the content of a region can be encoded on a lower dimensional boundary. There are even more speculative concepts involving new structures near the horizon. At present, there is no direct experimental way to distinguish between these possibilities. We are left with a situation where theory strongly prefers that information be preserved, but the mechanism remains uncertain. The question extends beyond black holes. As the universe evolves toward higher entropy, as structures break down and gradients flatten, we can ask what happens to the detailed record of what once existed. Galaxies form and merge. Stars are born and die. Planets change and erode. Over time, the arrangement of matter that once supported complex structures is altered. The information is not necessarily destroyed in a strict quantum sense, but it can become so widely dispersed and entangled that no observer could feasibly recover it. In a universe where dark energy dominates, this dispersal plays out against a backdrop of growing separation. Voids widen, clusters become isolated, and the overall trend favors uniformity on large scales. Black holes, once the final repositories of collapsed matter, themselves slowly radiate away over spans of time that dwarf the current age of the cosmos. Each step moves the universe towards states where differences matter less, where configurations look increasingly similar when viewed coarsely. Heat death is a phrase used to describe this far-off condition. It does not mean that nothing at all happens, but that there are no large-scale free energy gradients left to drive organized processes. In such a state, the universe would be close to equilibrium on every accessible scale. Any memories encoded in structure, any records etched into matter, any traces preserved in complex arrangements would have been transformed many times over. From the standpoint of everyday experience, this feels like erasure. The specific patterns that once existed are no longer available to be read. The universe cannot easily be asked what it once contained, because its contents have blended into forms that no longer retain distinct markers at accessible resolutions. Information, while perhaps preserved in the deepest formal sense, becomes practically unrecoverable. This long view includes our own presence. Our thoughts and actions, our instruments and archives, are patterns in matter and energy. Over long enough spans, they are subject to the same processes as any other structure. Erosion, dispersal, transformation under physical laws. The cosmos does not single them out for special treatment. They participate in the same unfolding as stars and galaxies. At the same time, the present moment occupies a special position in the story of structure. The universe is old enough for galaxies, clusters, and the cosmic web to have formed. It is old enough for heavy elements to have cycled through multiple generations of stars, making planets and chemistry like ours possible. Yet it is not so old that expansion has erased the broader pattern from view. Relic light from the early universe still reaches us. Distant galaxies are still visible. The large-scale web still imprints itself on surveys. We live in an era when the observable universe acts as a wide archive. Background radiation carries a snapshot of early conditions. The distribution of galaxies reveals how matter has flowed along filaments and away from voids. The motions of distant supernovae show the influence of dark energy. Together, these observations allow us to reconstruct a coherent picture of cosmic history, at least in outline. In future epochs, much of this archive will be gone from view. As expansion continues, galaxies outside our local bound region will slip beyond the event horizon. Their light will no longer arrive. The cosmic microwave background will stretch to wavelengths so long and faint that it becomes effectively undetectable. The evidence for an expanding universe, for a hot origin, for a rich surrounding web, will gradually move out of reach. Observers in that distant future, if they exist, may see a much smaller stage. Their sky could be dominated by a single bound group of galaxies, with little indication of anything beyond. Without access to the larger pattern, they might infer a universe that is static and limited in extent. The deeper history would still have occurred, but its traces would no longer be accessible to them. From this angle, our situation has a particular character. We inhabit a narrow interval when structures are abundant, and the evidence of their origins is still arriving. Before this, the universe was more uniform, with fewer complex forms. After this, it trends toward greater separation and smoother distributions. We find ourselves in a band of time when both richness and visibility coincide. In such a setting, questions about information and meaning emerge naturally. What does it imply that, in the far future, The record of what has happened will be diluted and hidden within high-entropy states. What does it imply that even now, our access to the full content of the universe is limited by horizons and by the finiteness of our perspective? The laws that govern matter and energy do not answer these questions directly. They describe how systems change, not how they should be interpreted. What we can say is that, at this moment, patterns exist. Galaxies arc across space. Voids extend in wide regions. Background light carries impressions from an early, dense state. Within one small corner, a species capable of forming models and stories has arisen, able to trace some of these patterns and to link them together into a shared understanding. The universe does not record this understanding separately from the processes that gave rise to it. It is another configuration of matter and energy, another arrangement within the whole. Over long times, it will be transformed. Like everything else, the physics that governs stars and black holes governs this too. Yet while this configuration persists, it allows a particular kind of awareness. We notice that most of the cosmos is space. We notice that dark energy guides the expansion, that voids widen, that structures thin. We notice that information is entwined with these changes, sometimes preserved in formalisms, sometimes hidden by practical limits. All of this noticing happens within a brief interval, on a small world, inside a galaxy that drifts through a vast web. The universe continues to evolve, indifferent to how often it is observed or described. Expansion proceeds. Entropy increases. Structures change. Information flows into ever more complex entanglements. Our position within this process is temporary. But while it endures, it provides a vantage point from which the whole can be contemplated. As time moves forward and distances grow, the details will continue to blur, and records will steadily fold back into the general fabric. For now, though, the patterns remain distinct enough to be seen, traced, and held in awareness, for as long as the present moment allows before it. 2. Joins the wider drift of the universe toward more uniform states. All around our planet, a new generation of observatories is turning outward, tracing lines and shapes across the sky. Together, they are building an atlas of the universe at a moment when that atlas is still possible. While distant light still reaches us, and the large-scale pattern has not yet faded beyond the edge of what can be known. One of these observatories is Euclid, a spacecraft that moves slowly around the Sun along with Earth, watching half the sky beyond the bright band of our own galaxy. Euclid records the shapes and distances of billions of galaxies spread across most of cosmic history. In its images, we see not only sharp points of light, but delicate distortions, faint arcs and rings where gravity has bent light on its way toward us. The invisible mass of dark matter, though it does not shine, leaves its mark by curving the paths of photons. Euclid reads those curves as clues, piece by piece. It reveals where matter has gathered into filaments and clusters, and where it has left wide regions of space nearly empty. The cosmic web, which we once inferred from smaller surveys of 1 million or so galaxies, becomes clearer and more continuous. Thin threads of structure cross vast distances, while the spaces between them stretch as voids that occupy most of the volume. As these maps grow more detailed, we watch how the web changes over time. Galaxies seen at different distances show us different eras, and Euclid lets us compare how structures looked when the universe was younger with how they look now. We notice how the expansion driven by dark energy has influenced the pattern, how filaments have thinned and voids have widened. Ordinary matter, which makes up only a small fraction of the total, follows the scaffolding of dark matter and responds to a background of dark energy that guides expansion on the largest scales. The result is a portrait of a universe where islands of structure are drawn out against a wide, open background, and where that openness gradually strengthens. On the ground, another project adds depth to this picture. The Dark Energy Spectroscopic Instrument, or DESI, sits atop a telescope that can sample the light of thousands of galaxies at once. Where Euclid measures shapes and broad colors, DESI measures spectra, splitting light into fine patterns of wavelength. From those patterns, we infer distances and motions. Over a few years, DESI has built a three-dimensional map of millions of galaxies and quasars, reaching far back toward the early universe. Within this map, subtle ripples in the distribution of matter act as markers of scale, helping us track how quickly space has expanded at different times. When these measurements are combined with observations of the cosmic microwave background and supernovae, they hint that dark energy may not behave as a perfectly constant influence. There are suggestions, still being tested and refined, that its strength could have changed slightly over recent cosmic epochs. If that is true, then the future evolution of expansion may be more varied than a simple, unchanging acceleration. The broad tendency towards separation and widening voids would remain, but the exact way that trend unfolds could differ from our earliest expectations. Over the next years and decades, more information will arrive. Another space telescope, the Nancy Grace Roman Space Telescope, is being prepared to observe a vast number of Type Ia supernovae, the same kind of stellar explosions that first revealed accelerated expansion. Each of these events acts like a luminous marker at a particular distance and time. By observing so many of them across a wide span of cosmic history, Roman will allow us to trace the expansion rate with finer precision. At the same time, it will measure the subtle stretching of galaxy shapes across large regions of sky, another way to read the influence of dark matter and dark energy together. In this way, Roman becomes a storyteller for the history of expansion, gathering thousands of separate flashes and weaving them into a smooth curve that shows how the universe has changed from its youth to its present form. With Euclid, DESI, and Roman working together, we are in an unusual position. We can measure the web of structure, the motions of galaxies, and the history of expansion all at once. We can see that dark matter forms the underlying framework of filaments and clusters, that dark energy drives accelerated expansion, and that most of what exists is not made of ordinary atoms. Our own local group of galaxies remains bound by gravity, even as more distant systems gradually slip toward and beyond the cosmic event horizon, the boundary beyond which their light will never reach us. Current evidence still points toward a very long, slow fading of activity, a future sometimes called heat death, where structures persist locally, but energy becomes increasingly dispersed over almost unimaginable timescales. Alongside these surveys of structure and expansion, another observatory looks back toward the earliest galaxies. The James Webb Space Telescope, with its infrared eyes, can see light that has traveled for more than 12 or 13 billion years, stretched by expansion into longer wavelengths. In its observations, we encounter galaxies from the first billion years after the Big Bang. Some appear surprisingly bright and massive, forming stars at rates that suggest rapid early growth. At first glance, they seem more developed than simple models of structure formation might predict for such an early time. Follow-up observations and careful analysis are refining these initial impressions, but the core lesson remains. The universe is capable of building complex structures quickly, and the early stages of the cosmic web may have been more varied than we once assumed. In Webb's images, we see knots of young stars, irregular shapes, and turbulent regions, rich in gas and dust. These are not calm, settled spirals like our Milky Way, but energetic, crowded systems, still in the process of taking shape. Their existence reminds us that our models, while powerful, are approximations. They capture broad trends, like the dominance of dark matter and dark energy, and the web of filaments and voids. But they do not anticipate every detail. Unexpected galaxies prompt adjustments. The overall story remains. Most of the cosmos is space, rather than matter, and structure emerges where conditions allow. Yet the pace and texture of that emergence can surprise us. Beyond mapping structure and watching early galaxies, we are also beginning to listen for subtle signs of technology in the atmospheres of planets around other stars. Instruments like Webb and future telescopes on the ground and in space can separate starlight from the faint glow of planets that orbit them. By passing that light through spectrographs, we can search for particular gases. Some of those gases can be created by geology or biology, while others are strongly associated with industrial activity. Molecules used in manufacturing or as refrigerants on Earth, for example, have distinctive patterns of absorption. If such substances were present in large amounts in an exoplanet's atmosphere, they might leave signatures in the spectrum that we could notice from afar. This approach adds another channel to the long search for other civilizations. Instead of relying only on deliberate radio messages, we also look for unintentional traces in the chemistry of distant skies. A planet with a thick, oxygen-rich atmosphere or with unusual combinations of industrial gases might hint at processes that go beyond natural background. The same telescopes that map the cosmic web and probe dark energy can, in principle, contribute to this quieter search, examining the atmospheres of worlds that lie on the thin filaments of galaxies scattered through space. All of these efforts take place during a particular window. The cosmic microwave background, the faint afterglow of the early universe, still reaches us from all directions, carrying information about conditions shortly after the Big Bang. Distant galaxies are still visible as small, red-shifted smudges, revealing the larger environment in which our local group resides. Technosignatures, if they exist around nearby stars, can still reach us before expansion dilutes and stretches their signals beyond recognition. The same physics that will one day narrow the observable universe currently allows us to see far and measure deeply. In this sense, the instruments now being launched or planned can be thought of as among the last wide eyes of the universe, at least from our position. They will not stop the expansion, or halt the growth of voids, or change the ultimate balance between matter and space, but they can trace the pattern with great clarity. While it is still available to be traced, they can map where matter has gathered and where it has thinned, measure how dark energy has influenced that process, and search quietly for any hints that other minds have also stared outward from their own small islands of light. As their observations accumulate, the atlas grows more complete. The lines of the cosmic web become more sharply drawn, the history of expansion more finely measured, and the range of possible futures more carefully outlined. We still see a universe in which ordinary matter is a minority, in which dark matter and dark energy set the overall stage, and in which our bound group of galaxies moves through a much larger, gradually thinning environment. Within that environment, these telescopes continue to watch and to record, turning remote light into understanding, and tracing the structure of a cosmos that, over long ages, will become harder to read from any single point within it. As we follow the widening voids outward, it is natural to wonder not only what the universe looks like now, but what it is moving toward. For a long time, it seemed that the answer might be settled. An ever-thinning cosmos, expanding under the steady push of dark energy, drifting toward a very distant heat death. Then new measurements arrived, and the outline of that destination became less fixed, as if the horizon of time had softened and blurred. Recent surveys that trace millions of galaxies, together with observations of the afterglow of the early universe and distant supernovae, hint that the push we call dark energy may not be perfectly constant. When these data are combined, they suggest that the expansion may once have been slightly stronger than it is now, perhaps reaching a peak and then weakening by a small amount. The result is not yet a verdict. It is more like noticing that a river current, thought to be uniform, might have begun to slow very slightly in some long stretch downstream. If this hint holds up, it carries a quiet consequence. Many of the firm statements we make about the far future of the cosmos would need to be softened into possibilities with different weights, rather than a single fixed outcome. The vision of voids growing forever, with expansion never easing, and heat death as the only destination, becomes one scenario among several. The universe's long future is still open enough to hold more than one ending. For now, three broad possibilities frame most discussions. In the first, expansion continues and structures keep thinning. Galaxies drift apart, stars burn through their fuel, and over immense spans of time, energy spreads out so thoroughly that new structure can no longer form. This is the heat death or big freeze picture. No drama, no sudden change, just a gradual fading of activity as the universe becomes ever more dilute. In the second, expansion does not last forever. If the influence of dark energy were to weaken enough, or if the total contents of the universe favored it, gravity could eventually pull everything back together. In that big crunch scenario, the cosmos would slow, halt, and then reverse, with distant galaxies turning around and falling inward over timescales beyond ordinary imagination, until dense conditions return. The third possibility lies in the opposite direction. If dark energy grows stronger with time rather than staying almost constant or weakening, its influence could overwhelm every other binding force. In that case, expansion would not only carry galaxies apart, but could, in principle, tear apart clusters, individual galaxies, and even smaller structures. This has been nicknamed the Big Rip, a universe where the stretching of space accelerates ever more strongly, changing the fabric of structure from the largest scales downward. These three paths depend on how dark energy behaves, whether it holds steady, fades, or intensifies. At present, the most widely supported models still favor a very long, slow drift toward a thin, cold universe. The emerging hints that dark energy might be evolving add nuance, suggesting that we are not yet in a position to exclude other fates with complete confidence. At the largest timescales, our predictions must remain provisional. Beyond these classic paths, some theories explore more intricate possibilities. In certain models, the universe does not end with a final freeze, crunch, or rip, but cycles. Expansion could be followed by contraction, which could in turn lead to a new expansion, in a sequence sometimes called a big bounce. Other ideas propose that dark energy could change sign or behavior, allowing the cosmos to reverse course after a long, expansive phase. These cyclic scenarios are mathematically consistent in some frameworks, but direct observational support is still missing. Our horizon is finite. Light can only have traveled so far since the beginning of the expansion we can see, so if there were previous cycles, their traces might lie forever beyond our reach. The universe could have experienced earlier rounds of birth and transformation, and yet the observable region around us might carry no clear memory of them. This limitation is not a failure of our instruments. It is a feature of space-time itself. Just as the event horizon around a black hole hides certain regions, the finite age and size of our observable universe hide whatever may lie beyond its boundary. The question of cycles, rebounds, or other phases remains present as a possibility, but one that is lightly held, waiting on evidence that may or may not ever arrive. All of these scenarios unfold on timescales that are difficult to grasp. Cosmologists sometimes divide the universe's history into eras: the age of bright stars, the age of dim remnants, the age of black holes, and finally an age of diffuse darkness. The period we inhabit, when stars are actively shining and galaxies are richly structured, is only one band in a much longer sequence. An analogy can help. Imagine compressing the full life of the cosmos into a single day. In that compressed day, the era when stars burn and galaxies form intricate patterns occupies only a thin slice around the middle. The brief span of human history is a narrow line within that slice, so small that it nearly vanishes. Most of the day ahead would be filled not with new bursts of activity, but with the slow transformation and fading of what already exists. From this vantage point, our current moment appears unusual. The universe is old enough to have formed complex structures, yet not so old that those structures have fully thinned out or slipped beyond the horizon. We can still see the afterglow from the early universe. We can still map the cosmic web. We can still detect distant galaxies before expansion carries them out of view. Our window is narrow, but it is open. As new observatories begin their work, they aim to refine our understanding of dark energy and cosmic structure. Projects designed to measure galaxy positions with higher precision, to watch how space bends light, and to trace the expansion history in finer detail will all contribute. Each new data set slightly reshapes the contours of our expectations. None has yet delivered a final verdict on the universe's fate, and it is possible that none ever will, in a complete sense. This lack of final certainty is not a flaw in the picture. It is part of the nature of an active science. Our descriptions of the far future rest on extrapolations from what we see now. As that view sharpens, extrapolations change. Some scenarios become less likely, others more plausible, and some remain on the fringe of possibility, neither confirmed nor entirely excluded. In that light, uncertainty becomes another feature of the cosmos we inhabit. We can describe how voids grow, how horizons narrow, and how entropy shapes structure. We can model different paths the universe might follow under different assumptions about dark energy. Yet the final outcome remains unwritten, because the information needed to decide between all options is not fully in hand. This open-endedness quietly reshapes the way we think about the cosmic void and the long fade of heat death. Rather than a closed destiny, they become a prominent, well-supported path among several. Grounded in current measurements, but still subject to revision, the void may continue to widen, or expansion may change its character over spans of time that dwarf any era we can directly probe. For us, living within a brief luminous interval, the important fact is not which distant scenario ultimately unfolds, but that we have access to this slice of cosmic time at all. We can watch galaxies recede, trace filaments across the sky, and listen for the faint microwaves that carry memory from the universe's earliest moments, all before those signals are redshifted beyond reach or hidden behind horizons. In the background, the future remains open enough to hold multiple possibilities. Our models sketch them in broad strokes, aware that the details may shift. The universe continues its expansion. Structures continue their slow transformation, and our understanding moves with them, always partial, always in motion, as the wide fabric of space and time stretches quietly on. As this journey comes to a close, what remains is not fear, but understanding. The universe is not empty because something is missing, but because emptiness is its natural state. Galaxies, stars, and worlds are only temporary islands rising within a vast ocean of space that continues to expand. Emptiness does not stand in opposition to life. It surrounds it and shapes the conditions in which life can exist. Through immense distances, through cosmic voids, through the expansion guided by dark energy, we begin to see that the universe is not moving toward drama, but toward a long, enduring stillness. Thank you for accompanying us on this slow voyage, for listening to the stories whispered from deep space. And if you wish to continue exploring the surprises, the unanswered mysteries, and the quiet yet meaningful dark regions of the immense universe, stay with us in the journeys ahead. Because beyond the emptiness, there is still so much waiting to be understood.